Hello, thank you for joining in on this presentation. Today we will present a tool for characterization of grasp performance using a sensorized glove system. The goal of this study is to develop a grasp performance system using a sensorized glove. We base the motivation of the study from the statistics provided by CDC that 795,000 people in the United States suffer from the effects of stroke every year. And of all the patients diagnosed with stroke, 88% of the patients experience hemiparesis or partial paralysis of the upper limb. However, the diagnosis of any grasp impairments are heavily dependent on the visual inspection of physicians and therapists and relating questionnaires, as provided by Barker et al. Thus, we present an objective quantitative measurement of grasp performances in this work, where we utilize a sensorized glove that measures grasp poses and contact forces simultaneously. To characterize grasp pose and contact dynamics simultaneously, we have used a pre-made tactile pressure sensing glove, the tactile glove by Pressure Profile Systems, and modified it such that a set of electromagnetic trackers can be mounted. The grasp pose is characterized by tracking the Cartesian coordinates of the fingertips, the wrist, and the base of the thumb using a set of electromagnetic trackers powered with the TrackStar 3D guidance system by Accession Technology. The contact pressure distribution at the palmar side of the hand is measured using the tactile glove, embedded with 52 capacitive pressure sensors in the nylon fabric glove. The glove is capable of measuring force values between 0.04 newtons and 70 newtons at a rate of 40 Hz. To validate the measurements taken with the tactile glove, the system integrity was tested with the Instrong force testing system. First, we molded a silicone hand with Tor harness similar to that of the outer epidermis of the human hand and was inserted inside the tactile glove system. Then, the tactile glove inserted with the silicone hand was applied 10 cyclic pressure tests with the Instrong tester. For consistent placement of the EM trackers on the tactile glove and the objects for each trial, non-metallic mounts composed of 3D printed thermoplastic elastomers and nylon screws were fabricated. And this figure shows the data flow diagram of the grasp characterization system, where we have the tactile glove mounted with the TrackStar 3D guidance system, and the force data and the position data are mapped simultaneously into a combined data storage, which then generates a graphical representation of the grasp poses formed by the human subjects. To visualize the grasp dataset, a human subject study was performed on 9 subjects, where each subject was to grasp 10 random objects from a pool of 36. The protocol for this study was, first, the subjects are briefed about the process of the study and are asked to read and sign the consent form. Then, subjects wear the sensorized glove and are given 15-minute training periods. After training, subjects perform tasks specific to each object for 30 to 60 seconds. Once data are saved to archive after each task, EM tracker on the object is relocated to a new object. Finally, after repeating data acquisition steps for all 10 objects, subjects are asked survey questions relating to their experience. To visualize the grasp dataset from human subject study for better understanding of pose and contact dynamics, the grasps are represented using animations that show the grasp poses and contact forces. The grasp pose was displayed using a skeletal representation of the hand, where critical contact points of the hand is represented with circles with different outline colors. The contact forces were visualized with color infills and arrows with its lengths proportional to the contact force magnitude. And you can see a sample video of a subject grasping a measuring cup. Here are some more video demonstrations of grasping tasks performed by subjects. As the subjects grab onto different objects, you may notice some of these circles lighting up, showing the contact forces on those points. The brighter colors are observed on the thumb and index portions, suggesting a high functional contribution from those parts. Thank you very much.